So Euler knew that this series converges absolutely for sigma greater than 1, or the real part of S greater than 1, by the comparison test with the integral of 1 over x to the sigma dx, which is from 1 to infinity, which converges again for sigma greater than 1, and it doesn't converge for sigma equal to 1, because that's the harmonic series. And diverges. And that's the key thing in the argument. As sigma approaches, or as S approaches, it gets larger and larger, because if you take S equal, you get the harmonic series. So what Euler discovered was this this beautiful product formula for it, and we now call that the Euler product. Although he had a lot of product formulas, this is just one of the many that he had found, and he didn't know that this was the most important at the time, which is that for the real part of S greater than 1, zeta of S is given not just by an infinite sum, but it's given by an infinite product over the primes of or minus beta minus S inverse. So that means, what is this term? If you expand that out, when the real part of S is greater than 1, the absolute value of beta minus S is less than 1. And so you can expand this out in it's a geometric series. So this is the product over P of 1 plus 1 over P to the S plus 1 over P to the 2S. And this is a convergent series because it's smaller than the 1 over the n to the S series. It's a piece of it. So it's given by an infinite product. All right, well, why is that? Well, if I just one term of this product, that's the sum over all the things that are powers of P. If I took the product of two things of that sort, and I multiply it by 1 plus 1 over q to the s, plus 1 over q to the 2s. And again, in the region of convergence, you can take the product and rearrange the terms. It's absolutely convergent. So always for S, real part of S greater than 1, this is given by something like this: 1 over P to the S plus 1 over Q to the S plus 1 over PQ to the S plus 1 over P squared Q to the S, etc. Namely, that would be this term times this term plus 1 over PQ squared to the S plus 1 over P squared Q squared to the S. You get the idea. You just take the product of all the terms, and you get, so this becomes the sum over 1 over m to the s, where m has the form p to the a, q to the b. So just one of them would just be prime powers. If you took the product of two, you get the sum over 1 over m to the s for all the integers that were. And more generally, if we took a finite set of primes, and we took the product over the p in s of this 1 minus p to the minus s inverse, we get the sum of 1 over m to the s, where m was a product p1 to the a1, pk to the ak, and these were the primes in s. So this is a finite product, and you get this infinite sum. Okay, and then Euler said, well, now let the set get larger and larger and larger, and well, this thing converges as s goes to infinity. This converges to the sum of 1 over n to the s for all n, because, and that's the argument, every n is uniquely a product of primes. And these terms, this series for s bigger than 1 is always less than this, so it's a monotone sequence that converges to this. And this converges to some fixed number, and consequently this product converges to that number. And that's the equality. So Euler's theorem is no more nor less than an analytic expression of the fact that every integer is uniquely the product of primes. But it has very powerful implications, because we know from the study of the harmonic series that this goes to infinity as s goes to 1. So now let's just take real values of s. And therefore, this series goes to infinity as s goes to 1, because these things are equal for s bigger than 1. And therefore, as Euler observed, since the log is an increasing function that goes to infinity, if we take the log of both sides, that goes to infinity. Goes to infinity as s goes to 1. And since log is continuous for an infinite product that converges, this log is the sum over the primes p of the log of 1 minus p to the minus s inverse. And that infinite sum goes to infinity as s goes to 1. Okay, now Euler uses the power series for, the nicest power series is minus log of 1 minus x, where you put two minus signs in, and that is x plus x squared over 2 plus x cubed over 3 plus. So this is for the absolute value of x less than 1, which it certainly is if the real part of s is greater than 1. So Euler puts this power series in and substitutes p to the minus s for x. And since it's log inverse, that's minus, I could have written it like this. And it produces so this is the sum over p, the sum over k greater than or equal to 1 of 1 over k times p to the ks. Okay. That's what I get if I put p to the minus s into the power series for log of 1 minus the log of 1 minus x. Okay, again, everything is absolutely convergent, so you can rearrange terms. And Euler says, well, let's break this into two pieces. We take the piece where k is equal to 1, so now we sum, instead of first over the primes p, we sum first over the k equal 1, so that just gives 1 over the s over p, this is the k equal 1 term. And then we have all the other terms, which I'll just write sum over p and k greater than or equal to 2 of 1 over k p to the ks. Okay, now this combination goes to infinity as s goes to 1. We're trying to show that this term goes to infinity as s goes to 1. That's the sum of 1 over p. So it suffices to show that this series, which is a double sum over primes and k, that this remains bounded as s goes to 1. And that's what he proves. Okay, and in fact, we're going to show it's less than 1. So let's see how we do this. Well, it's certainly bounded, whatever this is, in absolute value, it's certainly bounded by the series sum of 1 over p to the ks, or k greater than or equal to 2 and primes p, because dividing by a number bigger than 1 only makes the terms smaller. So if we can show that this series is bounded as s goes to 1, we're in good shape. Okay, well, what is this series? Well, let's write it out, the term for a fixed prime p. This would be 1 over p to the 2s plus 1 over p to the 3s plus 1 over p to the 4s. So that's pretty close to what we had studied before. It could be written as 1 over p to the 2s times 1 minus 1 over p to the s inverse, right? 1 minus p minus, yeah, right. Now let me write it like this so I can actually do it. 1 over 1 minus p minus s. Okay, and now I distribute the p to the 2s as, so this is just 1 over p to the 2s minus p to the s, right, that term for a given prime p. And that is less, because s is bigger than 1, that's less than 1 over p times p minus 1, right? I mean, it's p to the s times p to the s minus 1, so it's less than p times p minus 1. So this whole thing, because I have to sum now over the primes of p, is less than the sum over p of 1 over p times p minus 1, which is certainly less than the sum over all integers n of 1 over n times n minus 1. And it's a cute exercise to show that this sum is equal to 1. I'll let you guys go that one yourself. That's a telescoping series whose sum is actually equal to 1. So in particular, this part of the sum remains bounded and bounded by 1 as s goes to 1, and consequently this has to go to infinity as s goes to 1. And the next question you might ask is, how fast does it go to infinity? So Euler didn't do that, but we're going to show, because we're going to need it for a second, and we're going to need a little later, that this behaves in the same way as the log of 1 over s minus 1 as s goes to 1. And that's what you need to show that that's the sum diverges like log x. Okay, how do we show that this sum? Well, this is the log of the zeta function. So what we're going to prove, we're going to actually see what the zeta function behaves like. And this is a more modern theorem where you can find the proof in all the books. Theorem is that, and this is the first time we're going to use some complex analysis, that this is 1 over s minus 1 plus a function f of s with f of s holomorphic for s, real part of s greater than 0. So it explains what's going wrong with the zeta function at s equal 1. Namely, it has a meromorphic continuation to this half plane. So it's given, again, here's the complex numbers, here's s equal 1. It's given by a convergent series in this half plane. At this point, the series is not convergent. But what this theorem shows is that it has a meromorphic continuation to the real part of s greater than 0, to at least this region. And the reason it didn't converge at s equal 1 is because that function, that meromorphic function, has a pole at s equal 1. Meromorphic in real part of s greater than 0, simple pole at s equal 1, and the residue of that simple pole is 1. So we're going to prove that theorem, or at least sketch it. In fact, we're going to see later on, when we get to the work of Riemann, that this function has a meromorphic continuation to the entire complex plane. This was outside of the language that Euler spoke. Euler didn't deal in complex analytic functions, and he didn't know about holomorphic continuation or anything like that. That came later with Cauchy and Riemann. But since we're doing the sum of 1 over p, we might as well see how fast it diverges. And once you have this, then the log of zeta function, well, the log of a holomorphic function is holomorphic, if you pick a branch of a logarithm, and so it diverges like the log of this polar term. Okay, so how do we do this? So this is the kind of beautiful analytic number theory trick that you use all the time. So first of all, you have to identify the function 1 over s minus 1 as an integral. All of these analytic continuations, meromorphic continuations of these infinite series are going to be by finding an integral representation of the infinite series. Some kind of integral, which when you work it out, turns out to land you right on that series. So first we're going to find an integral representation for 1 over s minus 1, and I claim it's the integral from 1 to infinity of x to the minus x dx. Okay, why? Well, because we know the fundamental theorem of calculus, and this is x to the minus s plus 1 over 1 minus s, evaluated from infinity to 1. And this is taking s initially real, but you can do it complex. And when you take s equal to infinity, this tends to 0, and you would take s equal to 1. This is x to the 0, which is 1 over, whoops, what did I just do wrong? Is that right? Yeah, 1 over 1 minus s, except there's a minus sign in front of it because of the fundamental theorem of calculus. Right, okay. So there's an integral representation of 1 over s minus 1. Of course, now we can write this integral as the sum from n equal 1 to infinity of the integral from n to n plus 1 of x to the minus s dx. Right? And so, at least where we know the zeta function is defined, zeta of s can be now written like this. 1 over s minus 1, I'm going to add it and subtract it. This is for the real part of s greater than 1. 1 over s minus 1 plus the sum from n equal 1 to infinity of 1 over n to the s minus the integral from n to n plus 1 of x to the minus s dx. This infinite sum, again, converges for s bigger than 1 because it converges to this integral, which is well defined. And so I've added and subtracted 1 over s minus 1 to the zeta function. And now I rewrite this as an integral. The integral from n to n plus 1 of n to the minus s minus x to the minus s dx. I mean, this is just the constant function on the integral. The interval has length 1, so the integral of it just becomes this n to the minus s. And this is now convergent for real part of s greater than 1, and this all holds in the region real part of s greater than 1. All right, now call this function maybe phi n of s. That function, this individual function, is holomorphic for s greater than 0. Just integrating a function which is holomorphic. So if we're able to show that this series converges uniformly on compact subsets, then we have a limit of holomorphic functions converging uniformly on compact subsets, and we claim actually it's holomorphic for all s, holomorphic for all s, and it converges, on claim it converges uniformly on compact subsets of the half plane where the real part of s is actually greater than 0. And so this sum converges to a holomorphic function, f of s, on the half plane, real part of s, greater than 0. And that gives the meromorphic continuation. I still have to prove that this converges, and you're going to see why I did this very clever trick to get a little bit more convergence than, okay. And so, again, we're using the theory of holomorphic functions here, and you need a little bit of complex analysis to say that if you have a sequence of holomorphic functions on a domain, and they converge uniformly on compact subsets of that domain, and they converge to a holomorphic function, and you can differentiate term by term, etc. None of that was available to Euler. Okay, how do we show that they converge uniformly in compact subsets? Well, let's estimate the absolute value of that integral. Okay, the absolute value of the integral from n to n plus 1 of n to the minus s minus x to the minus s dx. Okay, so the interval has length 1. So this is less than or equal to the maximum of the absolute value of n to the minus s minus x to the minus s on that interval, or x between n and n plus 1, right? Because the absolute value of the integral is less than the integral of the absolute value, and the integral of the absolute value is less than the maximum of the value taken on that interval times the length of the interval, which is 1. Okay, now we're going to do this the minimum value on that interval is 0, right? Because you take x to be n. So we can estimate the maximum value by the maximum minus the minimum is given by the mean value theorem. Namely, it's the value of the derivative somewhere on the interval. So what's the derivative of this function? The derivative of n to the minus s minus x to the minus s, well, this is a constant, so you don't have to worry about it with respect to s, is s over x to the s plus 1. Well, you guys got to check that. That's a remember that x to the minus s is e to the minus s log x, and so when you differentiate it, you get we have to take the derivative of this. So d by dx of it, let's see if I get it right, is minus s over x times x to the minus s. That's this e to the minus s log x, and then this is the derivative of this with respect to s. S is a constant, and the derivative of log x is 1 over x. So you get a higher power of x, and consequently, the maximum value of this is less than or equal to the maximum value of s on the interval divided by n to the real part of s plus 1, because right, the largest value is obtained when x is equal to n. As x gets larger, this gets smaller, and you get s plus 1. So when you take the absolute value, just get the real part of s plus 1. So the absolute values of these terms that we're trying to bound are bounded by this, and consequently, if we're in an interval where the absolute value of s is less than or equal to r, and where the real part of s is greater than or equal to epsilon, right? Then this can be compared to our original series, 1 over n to the sigma. And since sigma is bigger than 1, that's a convergent series, and so this is bounded on compact subsets. It converges uniformly on compact subsets of the real part of s greater than 0. By, again, comparison with the harmonic series. And that's the proof that the zeta function has a little bit of a meromorphic continuation. Once you remove this pole at s equal 1, you can represent it by a holomorphic function. Now this isn't very useful. And the reason it isn't very useful is you say, okay, I now have the zeta function defined on this larger region. Where does it vanish? Where does it vanish? Well, how could you ever decide that? I mean, it doesn't vanish when the real part is bigger than 1 because of this product formula. You can show that the terms in the product are never 0. But where does it vanish? Does zeta s vanish when, for example, 0 is less than the real part of s less than or equal to 1? And s is not equal to 1. I mean, obviously it has a pole at 1, but it might vanish elsewhere. For example, does it vanish anywhere on the line where real part of s is equal to 1? And we now know that that's not the case, but how would you ever decide that? Because you can study when these functions vanish, but how can you decide when some infinite sum of them vanishes? So this gives a continuation, but doesn't tell us much about the function. And the zeros in same function are, in some sense, the big question. The big question, to refine Euler's results on distribution of primes. But we'll come back to that later. Let's go to Euler's second great result, which was his formula for zeta of 2. As I said, that he discovered that before he discovered the Euler product, and that was what made his name. Okay, so his proof of this was completely illegal. And it was not only recognized as illegal nowadays, it was recognized illegal in Euler's day. Euler thought it was illegal, his contemporaries thought it was illegal, everyone thought it was legal, but they knew it was right. So they took it. So it's all based on the study of the function sine x over x. So sine x over x is given by a power series, because we know the power series for sine x. And in general, you have the odd powers of x divided by the factorials. So, does anyone know who discovered the power series for sine x? This is a great mathematical story.
Newton?
Newton, exactly. Do you know how he found it?
Zeros.
All right, so we might say, oh, he calculated the derivatives of sine x at x equals 0 and used the Taylor's theorem. But no, that's not how he found it. Newton had something called the binomial theorem, right? Newton knew how to do 1 plus x to the alpha, where alpha was no longer an integer, but could be a rational number or a real number. He had a binomial expansion for it, okay? So, but he also did 1 minus x, he could do any of this type of thing. So he took this, and he took alpha to be minus a half. In other words, he was studying 1 over the square root of 1 minus x squared. And he found the power series expansion for it, using his binomial theorem, okay? Then, he integrated this term by term to find the power series expansion for the integral of this, which is the arcsine function. Then he reverted that power series to find the power series expansion for its inverse, and found these 3 terms, and guessed the rest. That was Newton's derivation of the power series for sine x. So mathematics frequently works backwards. I mean, the first discovery of it is always quite awkward, and you know, and Newton just wrote this, etc. I mean, that's all he needed to do, because he knew, you know, he could recognize these coefficients, and if you wanted to compute one more, he could compute one more, because he could compute the power series for this as far as you wanted, and then he could compute the power series for the integral, and then he could revert it very painfully. So that's how he found that. Later, people realized, oh, well, of course, it's Taylor's theorem. Anyhow, we know sine x. So we know sine x over x. That starts 1 minus x squared over 6 plus x to the 4th over 120 minus the 7. Using the factorials. Okay? Good? So Euler said, look, let's pretend that this function is a polynomial, and for a polynomial, if I know its value at a point and I know where the zeros are, I can write a product expansion for it. So where does this function? Well, we know the value at x equals 0 is 1. And that's the classic limit formula that gives us this 1. And we also know that it vanishes at x equal to plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, etc. You might say, well, it also vanished, sine x also vanishes at x equals 0, but dividing by x got rid of that 0. Okay? So therefore, Euler felt that if things worked well for functions as well as with an infinite number of zeros, as well as it worked for polynomials, maybe this would be 1 minus x over pi, 1 minus x over 1 plus x over pi, 1 minus x over 2 pi, 1 plus x over 2 pi, etc. That would be the hope, that it would be given by
some kind of infinite product. And what he did was he didn't want to do a product over all integers, so he put the terms with pi and minus pi together, and with 2 pi and minus 2 pi together. So this becomes 1 minus x squared over pi squared, and then the next one becomes 1 minus x squared over 4 pi squared, and the next one becomes 1 minus x squared over 9 pi squared, etc. Okay? So his belief was that this function should have this product expansion. Seemed reasonable. And if it has this product expansion, but it also has this Taylor expansion, then you can equate the coefficients of x squared and x to, this is also an even function. You can, so this goes like 1. And then what's the coefficient of x squared? Well, you get 1 over pi squared, 4 over pi squared, 9 over pi squared. So you get minus 1 over pi squared, summation of 1 over n squared, equal infinity, times x squared. That would be the coefficient of x squared plus some coefficient of x to the 4th plus etc. And you'd say, well, look, the coefficients of x squared have to be the same, so this has to be the same as minus a 6th, and that gives you the sum of 1 over n squared is pi squared over 6. And then if you wanted to know what the sum of 1 over n to the 4th was, well, you have to work a little harder, because this coefficient of x to the but Euler had a lot of time on his hands. So the coefficient of here is 1 over pi to the 4th, the sum over m greater than n greater than or equal to 1 of 1 over n squared m squared, right? I mean, if I had I'd get an x to the 4th term from here, and an x to the 4th term from here, and an x to the 4th term from here, but I'd never have m is equal to n. Well, that term is 1 over pi to the 4th, if I didn't get this wrong, 1/2 of zeta of 2 squared minus zeta of 4. Namely, you take sum of 1 over n squared, you multiply it by the sum of 1 over m squared, and then you subtract 1 over n to the 4th, and that cancels out all the diagonal terms, and you're left with this once you divide it by 2. Okay, and that has to be equal to 1 over 120, and then when you already know what zeta of 2 is, you can solve for zeta of 4, and zeta of 4 turns out to be pi to the 4th over 90. And so Euler proceeded out in that way and found formulas for zeta of 2n. You could see that they were always rational numbers times pi to the 2n, and he made tables of these rational numbers, and that's going to become important to us later on, times a rational number. And he tabulated these for n less than or equal to 20, which required an awful lot of work because, I mean, this series is very simple, but each time you do another coefficient of this, you have to do all the previous coefficients like this one, and kind of a pain. Okay, so as I say, nobody was really happy with these proofs, and the next generation went completely insane with them. I mean, Abel was infuriated by them because they knew that they worked, but they weren't justified, and so people developed the theory of infinite products, and nowadays we usually prove this formula for the zeta function at 2n using the cotangent function, but I'm going to leave that aside. But the reason that Euler really believed the results, as I said to you, is he had calculated both sides of this. And it had very clever ways of calculating pi and very, very clever ways of calculating zeta of 2. And he found that both sides agreed to 20 decimal places, and They were both about equal to 1.6449340. He had more places. And so there was no doubt in his mind that he had gotten the right answer with an unjustifiable way. So I think it's even more interesting to show you how Euler estimated zeta of 2. So I'm going to do that for you. All right, and I'll let you guys read about the legitimate proofs of this in the literature. Because that was the beginning of what we now call the Euler-Maclaurin formula. And so, I mean, if you just think of it, suppose I took the definition of this, and I took the sum up to 10. So 1 plus a 4th plus a 9th plus a 16th plus 1 over 10 squared. And I wanted to know what that was equal to. I even did this. So that turns out to be 1.549769, etc. So you're off already by about a 10th. You know, the rest of the series sums up to about a 10th. So, you know, and you could try this up to 100, you could try it up to 1,000, you wouldn't get anywhere near this accuracy. So we have to have something extremely clever in mind. So he took the following point of view. Suppose we have a function f defined on the integers, so we know f of n. And we want to find the function s of n, which is the sum of the first all the way up to n. It's a new function, s of n. Okay. Well then, what does this function s satisfy? And Euler was interested in the case, because we're going to see a couple of examples of this, in the case where this function was not just defined on the integers, but had a sort of reasonable, both functions have reasonable extensions to a function on the real numbers and another function on the real numbers. Well, if you had this function on the real numbers, then it would satisfy the difference equation, s of x minus s of x minus 1 is f of x, right? Because the value, that would be the case of n plus 1 minus f of s of n would be just that, right? So you get a difference equation. And it also has the initial value that s of 1 is f of 1. And if you didn't like that initial value, you could take any integral initial value or more generally, s of n is this. So if you could find a function that satisfied this difference equation, and it had an initial value like this, then s of n would be the sum of f of n for all values, right? Okay, so Euler didn't have that many analytic tools at his disposal. He had really just calculus of one variable. And so he used this all over to try to solve this difference equation with these initial values. So what are some examples that we're going to do this for? Well, the famous example that had been solved by the time Euler came to this problem was the kth power function. Because then this s of n is 1 plus 2 to the k plus 3 to the k plus n to the k. And what his friend Jacob Bernoulli had proved was that this was some polynomial depending on k in n. For example, 1 plus 2 plus n is n times n plus 1 over 2. And Bernoulli had formulas for the sum of the squares and for the sum of the cubes, etc. So that was a famous example. All right. Another example that had been studied before Euler's time, but Euler was able to refine, was f of x is equal to the log of x. Okay, then, so then s of n is 1 plus the log of 2 plus the log of 3 plus the log of n, and since the log of a sum is the sum of the logs is the log of the product, this is the log of n factorial. Gives you the number of basically the digits in n factorial, and that was a problem that had been studied by de Moivre. And he had shown that this was about the same size. He didn't have an exact formula for it, but it was about the same size as n log n minus n plus 1/2 log n. We'll get there and show you how he did that. De Moivre's an interesting case. It's an example of how religious persecution often helps mathematics. So de Moivre, as you might imagine, was French. He was a Huguenot. But he had to leave France at the end of the 17th century when Louis XIV revoked the Edict of Nantes, which meant that if you were a Protestant and you lived in France, you were dead, basically. And so de Moivre went into exile. He had been a member of the Academy, a distinguished gentleman. He fled to England, where he couldn't get a job because, of course, he was French. Refugees weren't treated any better than they are now, except, so he had to make his living somehow, and he made his living gambling in the coffee houses of London. There was a lot of gambling in the coffee houses of London, and so to gamble successfully, he had to figure out probabilities, and he wrote the first book on probability theory. And Newton thought very highly of him, but couldn't get him a position. He said, de Moivre understands the calculus now better than I do. Anyhow, de Moivre had used calculus to obtain this estimate for the log of n factorial. And you can imagine that n factorial is a number that probabilists like to estimate, right? 52 factorial might be a good number to know. So he had obtained this estimate, and Euler was going to refine it by finding a better formula for log of n factorial using this method. And finally, what he's really going to apply it to is f of x is equal to 1 over x to the k. K bigger than 2. And then s of x, or s of x converges, or s of n, sorry, converges to zeta of k as n goes to infinity, right? Because you're getting 1 over 2 squared, 3 squared, 4, right? And so if he can get a good formula when f of x is this, and he gets a formula for s of x, or some approximation to s of x, he'll have a way of calculating zeta of the k, for k at least 2. And here you could do it for zeta of 3, zeta of 4. I mean, nothing was wrong with doing odd values either. Worked in all cases. Okay, so how did Euler do this? As I say, he had one tool at his disposal. He was going to do this using calculus. Let's start out by just using the integral. So the first thing he observed is that s of x is about I mean, if we took n, that would be about the integral from 1 to n of f of t dt. Again, you need the function to be reasonably behaved, because if I calculate this integral and I divide the interval from 1 to n, from 1 to 2, or 1 to 2 to 3, etc., and I take the values at the endpoints, I get this, right? Okay, and then so that why not say that we look for a solution where s of x is the integral from 1 to x. But if we want the right initial condition, namely s of 1 is f of 1, we better add 1/2 of f of x plus f of 1. Because if x is equal to 1, this is 0, and we want s of 1 to be f of 1, so we can do this. If you think about this, this is let me rewrite this again. This is like f of 1 plus the integral from 1 to x of f of t dt plus 1/2 f of x minus f of 1. That's a little more attractive to me. I mean, this is what you add to the integral formula if you use the trapezoid method instead of just the rectangular box method. All right? So that's where de Moivre's formula comes from, because that's all de Moivre did. He replaced this sum by an integral. He said, well, therefore, the log of n factorial is about f of 1, the log of 1, that's 0. Then I have to integrate from 1 to n of the log of t dt, and then I have to take plus 1/2 the log of n. Well, what's this integral? Well, you need to find an antiderivative of the log of t, and the antiderivative is t log of t minus t from n to 1, right? If you differentiate t log t minus t, I think you get log of t, right? I mean, let's do the multiplicative mode. You differentiate this, you get log of t, and then you have t times 1 over t, that's 1, and you subtract off 1. Okay, so you get n log n minus n plus 1/2 log n. And that's exactly what de Moivre's estimate was for the log of n factorial. So that's the first approximation. You replace the sum by an integral. Okay? That's this example. Okay, but we could also do it, if we didn't want to do this initial condition, but we wanted to do this initial condition where we had a little bit more data on f, we could also say it's about f of 1 plus f of n, and then we can take the integral from n to x of f of t dt, and then we take plus 1/2 of f of x minus f of n to arrange the correct initial condition, because in this integral it's 0 when x is equal to n, and we want it to be equal to this, so we have to have this to make sure it's equal to 0. Okay, so this was Euler's first approximation using the integral. But then he pushed this a little bit further. He said, well, let's suppose that we have the function s of x, and let's look at its Taylor expansion. Suppose we know s of x, and take the Taylor expansion at x equal a. So that's, of x minus 1. So that looks like this. S of x minus 1 is equal to s of a plus x minus 1 minus a, s prime of a, plus x minus 1 minus a squared over 2 factorial, s double prime of a, etc. Okay, now take a equal x. This is what Euler would always do. So a is supposed to be a point, but we take it to be the variable x. S of x minus 1 is s of x, because we see we want to compare s of x to x of x minus 1, plus, well, if a is equal to x, that cancels this out, so we just get minus s prime of x, right? Plus s double prime of x over 2 factorial minus s triple prime of x over 3 factorial, etc. And so he rewrote this as, let's rewrite it. Notice that we see like the exponential function, the power series, the exponential function coming in as an operator. So we could write this as, suppose I wrote it as like this, e to the d by dx of s of x. So I use the power series of e to the minus t, right? 1 minus t plus t squared over 2 factorial minus t cubed over 3 factorial, and I use that as an operator. So the first thing I get is s of x, then I apply this operator with a minus sign, minus s prime of x. I apply the operator with a plus sign twice to get s double prime of x, etc. Okay, so therefore, on the other hand, s of x minus s of x minus 1 is equal to f of x. So let's take this expression for s of x minus 1 and rewrite it like this, is equal to 1 minus e to the minus d by dx of s of x. So if we had the function s of x, the relationship, we'd get the function f of x back by applying this operator to it. So Euler said, well, let's just reverse that process. We're given the function f of x. Let's revert this to get the function s of x. And so he needs a new power series, not the power series for the exponential function, but essentially the 1 over the exponential function. See, s of x is going to be equal to 1 over 1 minus e to the minus d by dx applied to f of x. And I have to know what this operator looks like in terms of derivatives of f. Okay, so that led him to consider the following series. Actually, he put a t in it. T over 1 minus e to the minus t. So this power series begins with t. So t. So this power series begins with 1. And Euler worked out the terms of this power series. For a number of terms. And he wrote the coefficients, and he called them Bernoulli numbers after his friend Bernoulli, as bm over m factorial t to the n. So these are universal rational numbers that are determined by the exponential function. But they're complicated to compute because you have to work out this power series, then you have to work out the inverse power series. So each time you compute one, you have to know all the previous ones, etc. So this gives a table of Bernoulli numbers. So B0 you could sometimes call 1. B1 is a half. B2 is a 6. And then all the other odd Bernoulli numbers turn out to be 0. And then B4 is minus a 30th. And B6 turns out to be 1 over 42. So these, as I say, these are just fundamental rational numbers. It's clear they're rational because the power series here has rational coefficients. So when you invert it, it has rational coefficients. But until you work them out, you don't know what they are. But you might think they're always of the form 1 over an integer, but they're not. By the time you get to B12, you finally get a numerator. 691 over 2730. And B14, you might think they're always less than 1, but B14 is 7/6. That's the first one that's greater than 1, and after that, all of them are greater than 1. So Euler made expensive tables of these numbers once he realized that this series was important. And so then we can write s of x in terms of f of x, its integrals, and its derivatives. So formally, it would look like this. And that was the genesis of Euler-Maclaurin. So formally, since we have here, there's a t, this is 1 minus, you have to divide this by t, so it starts off 1 over t plus a half. Well, what's 1 over differentiation? That's integration. So it's the integral of f of t dt, that's the first term, up to x, plus 1/2, well, you divide this by t, then you don't apply the operator, so that's just the value f of x. And then you have plus 1/12 f prime of x. That's the operator applied once. Instead of t squared, you have a t here, t over 12. Then you have f triple prime over 720. Etc. That's his idea of, this is the function s of x. So if I had the function f of x, this was my original approximation of it using the integral. Well, if I went from 1 to x, I'd have to put f of x minus f of 1 to get the right initial value. And then I'd want f prime of x minus f prime of 1 to get the right initial value. And then I'd want f triple prime minus f triple prime of 1 to get the right initial value. And this part of the formula was what de Moivre had realized, etc. And Euler realized that you could get better and better estimates of s of x if you included the derivative of f, and the third derivative, and the fifth derivative, etc. Okay, now, again, there's no reason to just start at s of 1. We could do, so the final formula looks like this. If you take the initial condition at n, f of 1 plus f of n, this is for x bigger than n, plus the integral from n to x of f plus 1/2 f of x minus f of n plus 1/12, etc. All right, now this is a very useful formula. The first thing that Euler did with this formula is he recovered Bernoulli's polynomials. Because in the case where f of x is x to the k, eventually the derivatives become 0. You differentiate polynomial enough, you get 0. And so this gives a polynomial expression for s of x in terms of f of x. And when he worked it out with these Bernoulli numbers, they turned out to be related to the coefficients of the Bernoulli polynomial. But then he tried to do it for f of x is x to the minus k. Now here, no matter how many times you differentiate it, you're getting a non-zero function, and then you have to start worrying about the convergence of this series. And because these Bernoulli numbers start to grow, and we're going to see how quickly they grow, but I mean, once you get to here, they really grow very rapidly. It turns out the series isn't convergent at all. But that didn't bother Euler and his contemporaries. What Euler did was he said, well, we'll just go out as far as we need to in this until it starts to diverge, and then we'll drop it off. And that was the notion of an asymptotic expansion. So I'm just going to show you this for x to the minus 2. And how we computed it. I mean, it's unbelievable. So the integral of f is minus 1 over x. And then the derivative is minus 2 over x cubed. And the second derivative, which I guess we don't need, I guess we only need the third derivative. That turns out to be minus 4 factorial 24 over x to the fifth. So what does Euler-Maclaurin give us in that case? Well, let's take n equal 10. So it would say that s of x is 1 plus 1/4 plus 1/100th. That's what we had previously calculated, right? Plus well, we have to take f of 1/2 of f of x minus f of, where are we here? We have to do this. The integral from 10 to infinity. Now the integral to infinity of this is 0, so we just have to do plus 1/10. So this is the original formula. This is the integral, right? From 10 to infinity of minus 1 over x. And then we have to add plus 1/2 of f of x, which is 0, minus f of n, that was 100. So we take minus 1/2 of minus 1/100th, right? and then we get a 12 of, et cetera. Yeah, and when you do this, and you take the next term, it turns out to be equal to. So it's so we add a tenth, we subtract 1 over 200, the next term is 1 over 6,000. Everything is converging very nicely. The next term is minus 1 over 31 million. 3 million, sorry. Everything again starts converging well, and then things start to blow up on you, so you just stop at that point, and you add this number to this number to this number to this number to this number, and that's where you get zeta of 2 accurate to 20 decimal places. Go figure. I mean, it's a miracle. But Euler did this with the gamma function. He found the asymptotic expansion of the gamma function, and also did the zeta function at other points. So it's a very powerful analytic tool. And it just shows how far you get with calculus. I mean, again, to start off with this approximation, just using the integral and the trapezoid method, and to sort of realize that those are the first two terms of this expansion of the inverse of the exponential series, just unbelievable stuff. And he knew it worked because, oh, I meant to finish. How do we calculate pi? All right, I'll give you another trick. So Leibniz had done this, right? Leibniz had shown you that pi over 4 was 1 minus a third plus a fifth minus a seventh plus a ninth. That was the first one. We're going to see that this is also a formula about L functions, but we haven't gotten there yet. All right, so that looks like a good, promising series to calculate pi, but again, because it's an alternating series, by the time you get up to a ninth, you're within 1/11 of the answer, right? Because it alternates above and below a convergent alternating series. If this is the limit, the first term will be up here, and the next term will be here, and the next term will be here, and the next term will be here. It sort of converges in, and it's never further off than the next term. So just using the first 5 odd numbers, I could get you pi over 4 to the first decimal place. But in fact, I could get it to 6 decimal places, just using these terms. How do you do that? Well, here's a trick. You say, well, look, I mean, not only is the first term bigger than pi over 4, and the second term in the series, so pi over 4 is less than 1, but it's bigger than 2/3. Because then you're going to add a fifth to it, right? But it's closer. The second estimate is better than the first. So if you took the arithmetic mean of these two numbers, of the first and the second sum, that would still be bigger than pi, because the second term is getting closer to it than the first one was a bit above it. So if you take so if you take S1 plus S2 over 2, that's got to be bigger than pi over 4. And if you take S2 plus S3 over 2, that has to be less than pi over 4. So you get, again, by taking arithmetic means of the sums in this sequence, you get better upper and lower estimates for pi over 4. But if you think about it even more, let's call this thing T1 and this thing T2. The arithmetic mean of T1 and T2 is still bigger than pi over 4. I mean, this one is much bigger than this one is less. And so you take arithmetic means of the arithmetic means. You make yourself a little table, I suggest you do this, of all the possible sums up to 9, and then take their arithmetic means, and then take their arithmetic means, and then take their arithmetic means, and take the best number that's bigger and the best number that's lower, and you get 4 decimal places of pi. So Euler knew all those tricks. And this is just another trick of summing a series by adding a few terms from the Euler-Maclaurin expansion until you start getting nonsense. And well, suffice it to say that analysts have spent the last 2 centuries trying to make sense of this. And I'm not going to do it. But next time we'll pick up, and I'll show you even more amazing things that Euler did, completely unjustifiably, of how he studied the zeta function at negative integers. And proved, for example, that 1 plus 2 plus 3 plus 4 was minus a 12th. That seems unlikely, but that minus a 12th is related to this Bernoulli number of 1/6. So we're going to see some more magic that we did. And as I say, if you want to see a reasonable treatment of Euler Maclaurin, et cetera, you have to look in the, you know, what kind of analysis, a postal or something like that. Good? Okay, what time is it? People leaving? Good, time to stop. See you guys on Thursday.
就是那个从那个怎么 approximate zeta to
Yeah, it's not.